part on this computer. Okay, let's hide this thing. Hide login control. And here, let me. What? Mm-hmm. Oh, here it is. Perfect. Okay, guys, welcome. This is the 11th lecture of the FIS 140 for this semester. And let's see where we were left off. Yeah. Last lecture, we were looking at the problem of special relativity, the simultaneity, the time dilation, length contraction, and whatnot. And all of those things are related to light. Okay, so light it's a very important fact in the physics of the 20th century, and it's going to be a very relevant aspect that we will have to continue looking at it, because we have always had models to describe how lights work, but they are just a perspective of what light is. Okay, if you look, you know, it's like looking an object from one side and you see sort of a profile of something, but you can, by looking at the side profile, you cannot really tell what the object or the person is if you look at it from the front. So what we have been doing so far is describe model that sort of look at light from a certain perspective, from a certain side. So and today we're going to look to a different side of light, because light has always bringing to us new and interesting physics. Let me see if I could. No, I don't. Okay, here we go. So light is as I say here, is an axis for new physics. First of all, transport. We have a wave equation to describe electromagnetic radiation, and so we have a model associated with light that has to do with diffraction, that describe very well the transport of light from one part in space where the source is to actually where the excitations are seen, and the wave equation is a very good thing that we can actually use to understand phenomena, wave phenomena associated to light, that is diffraction from one side and interference. Okay, so this is very relevant fact here. Okay, in terms of, you know, all communication has to do with this, with diffraction, interference, and transport of electronic or digital information. Okay, the velocity of light was something very relevant in terms of redefining Galileo transformations, and we got to Lorentz transformation to include the relativistic effect. Okay, if it weren't by that, we couldn't be using GPS today, because GPS has to do with the synchronization of moving clocks. And the moving clocks are actually in the satellites, and satellites actually locate the position of a certain object by measuring the distance to the object with a particular clock and synchronizing it. Well, to actually get the position of somebody on Earth, you need your telephone to be connected to 3 or more satellites in space. And by measuring the distance from those 3 objects and you know, getting that information down, that is what allows you to localize yourself on the surface of Earth. If the clocks were not synchronized, the errors would be huge, and there will be no GPS system. If there is a way, if there is an example where special relativity has some bearing on some engineering related aspect, it's exactly in the global positioning system and synchronization of information there. The subject we're going to be looking at today is it's a bit different. It has to do with the interaction of light and matter. And so in this subject, you know, one famous guy that used to work with light, you know, produced an interesting model, proposed an interesting model is the model for the photoelectric effect. He actually, Einstein is less well known because of the photoelectric effect. He's well known due to relativity, but he actually got the Nobel Prize for his explanation of the photoelectric effect. And this is exactly what I'm trying to describe today. This is the physics of the beginning of the century, again, of the 20th century. And these are these very bright people that had very few technical, I would say, tools to actually understand the theoretical models that they were being proposed. But a good exception is the photoelectric effect that was already being seen in a few materials. Okay, let me get ahead here. No, I'm not going anywhere. Here we go. Here we go. So the photoelectric effects describes update later. Oops, I have to get out of here. Okay, that is working. No, something happened here. My apologies. Oh, I'm sorry. This program is updating PowerPoint.
Understandable.
I didn't realize that. I shouldn't have pressed the thing. Okay. Is it doing it well? Oh, come on. Go away. No. Okay, it's giving me the information that it's updating. It will open when it's finished updating. Let me see if I could do this. Okay, let me see if I can share this screen instead. Yes, I can share. I don't know if this will work though. Okay, here we are. No, it's not doing it. Let me get rid of this. Okay. And now view, enter full screen. Okay, I guess I will have this thing at the side though, because I don't think I can. Let me see. No, I cannot. Okay. Can I advance? Oh. No, I cannot advance the pages either. I don't know how long will this take. No. Oh, my apologies. Okay, well, I can let you know the story in the meantime. Hopefully this will end soon. And so the story in the meantime is the following. The thing that how lights interact with matter is essentially how lights interact with electrons. If you have let's say a piece of metal and you have many electrons that are moving inside, and what really happens is that the energy that is contained in light is absorbed by the electrons. And if the amount of energy is the right one, the electron can absorb enough energy to actually leave the piece of metal or material that is actually containing them. So the thing is, let me see if I could open this. No. Oh, it's working now. Okay, so the idea then is we have to look at electrons coming out of. Are you seeing a page? You're not seeing anything now, I assume.
What we're currently seeing, it's the apparently PPT or presentation selection in PowerPoint.
Okay. Okay, let me see if why is it not working? Okay, stop share. And now share screen, share this screen, share. Okay, there we go. And perfect, now it works. And here, let me get rid of this. Hide floating meeting, yes. This put at the corner here. Now I need laser pointer. Perfect. Now let's go to the next page and the next page. Perfect. So the photoelectric effect describes the interaction of a metal with short wavelength light. Why is short wavelength? What does it mean? Short wavelength, as we will see, means high energy. They are equivalent. So no matter the interesting thing is the following, that if the wavelength is not it doesn't have the right energy, and we will see what that means, it means that no matter how intense a beam of light is, it cannot remove electrons from a piece of material unless the frequency is very high. So that's something puzzling a bit, because the idea that we have in mind is that what we actually need to get an electron out of a piece of material is to deliver to it enough energy. And if I increase the intensity to the whole thing, I'm actually giving a lot of energy. So, and the electrons are the guys that are getting that energy because they can move easily. It means that after a while, the thing should have packed enough energy to come out. Okay, that is the classical model. And okay, here it is. And that is not exactly what is going on in this material. Okay, that is the classical picture that I have just described is mistaken. Okay, so let me describe with pictures here what it happens. So we have light that is incident on a material, and electrons come out. So that is exactly the definition of the photoelectric effect. So it's the photoelectric effect is actually ejection of electrons from a surface. For that to work, you know, you need a lot of electrons. So in general, the materials that are actually producing this or displaying this photoelectric effect are in general metals. But the electrons, as the model explains here at the bottom, are somehow bound to the atoms inside. So there is some. It's not simply like ask an electron to come out. You really need to deliver some energy to it to get it out. So to eject an electron, light must supply enough energy to overcome the forces holding them together inside the material. Okay. What I'm showing here is, let me move this guy this way. What I'm showing here is the actual experimental realization of this thing. So we have this thing, which is some sort of concave mirror that when light is incident from this side on it, it will focus almost all the light in the position of this wire here. This wire is where we want the electrons to come out. So the electrons come out of a cathode and no, what I'm saying here, no, let me see. The electrons come out of this thing here, of the material, the anode. The actual shape of this, I was confused before. My apologies. This is a metal piece where the electrons come out. Light is incident on it, and the electrons come out. The shape that this thing has is actually to focus the electron onto the wire where they are collected. So how do we know electrons come out of the material? Because we have to collect them, and we collect them in this material here that is the anode, and they come out of the cathode. And you know, since these guys are electrons, if you want to collect them all, you better put here a positive voltage. That's what is being done at the bottom here. You put a positive voltage here, so an electrons in this region of space, oh wow, there's positive charge over here, so I'm going to go there, and that's what happens, and so you can catch all the electrons coming in this direction. But you can also turn this power supply around. This is what has been done here, and actually repel some of the electrons. Why would you like to do that? You know, this is sort of the experiment, because if you put a voltage that is relatively low, negative voltage that is relatively low, and the electrons have a very high energy, they will arrive to the anode anyway. So they will overcome the potential barrier imposed by the negative voltage on the anode. But other guys that don't have enough energy will start going that direction, and then they will come back because they cannot overcome the barrier. They will be rejected by the negative voltage put on this electrode here. Okay. What do we do with that? We decrease the number of electrons that we measured. And what is the origin of the electrons? The origin of the electrons are the ones that are actually being illuminated out of the cathode. Okay, and then they are rejected by the anode in a way. Okay, so this is sort of the experiment, and let me show about the results now. No, this is the way it goes. Okay, so these are part of the results. This is VAC, is the difference in voltage between the anode and the cathode. Okay. When you put a positive voltage, this is in the repulsive mode, okay? But when this is reversed, when you put a positive voltage in the anode cathode, the anode is positive with respect to the cathode. What you end up doing is collecting all the electrons that comes out, okay? So let's look at the curve at the bottom. We have a constant intensity I of the light coming into the thing, and we're shining, and we have a positive voltage. We have a positive voltage. It means that every electrons that comes out of the material is actually collected. But what is the limitation? on the number of electrons that comes out. What is the limit for the current? Well, the limit from the current is essentially the intensity of light. How much light do you put in? If you put twice the intensity of light, you get twice the number of electrons coming out. Okay, but there's something very peculiar about this. Here it says that this experiment is done at a constant frequency. The F is the frequency. I call the frequency nu in part of the Greek letter nu in part of my notes. So F and nu are simply equivalent in this. I did that before looking at the figures, so my apologies. So nu and F are the same thing. So this is constant. So what does it mean that the frequency of the light is constant? It means that the light has only a single color. It's monochromatic light that is incident on the cathode. And this is what happened. No matter what the intensity is, the energy, what is V0 when the current is zero? When the current is zero, it means that the kinetic energy the particles will have on the surface of the cathode will be exactly canceled by the applied potential. It means no electron will be able to get to the anode because I am repelling them exactly. If I lower, let me see, if I raise the voltage a bit, I have a bit of a current. If I lower it, there's no current. So V naught actually is a measure of the maximum energy of the electrons coming out of that cathode. What I have just said is it's an important element of this particular model. This is the result of the experiment. So, and here, what do I, in this diagram here on the left, what do I have? I have, electrons will arrive at the anode, will arrive here only if they have enough energy to overcome the repulsive potential that I'm applying. I'm applying a repulsive potential here and at this place, and the electrons will be able to come here only if they can overcome the barrier imposed by the repulsive potential.
All right, so I've actually got a quick question relating to the model.
Okay.
Okay, there apparently seems to be a certain potential, or I'm not sure if we're measuring this in voltage, that the anode can have in order to accept what would be the energy. Otherwise, it would be repulsive. But with that repulsive potential, I'm looking at the like graph on the right side. Would it mean that at like negative voltages it would become repulsive?
Yes.
Or is all right.
Negative voltage are repulsive. It has the reference that the A is positive with respect to the C. If A is positive with respect to the C, is positive. When the thing is reversed, when the cathode it's more positive than the anode, is a reverse voltage. Okay, so that is the situation here. Okay,
perfect. Now I understood it better.
You have to be reminded also that, oh God, where's that? That's way back there. That the total potential energy of a particle, of a charged particle at a fixed potential is the product of the charge times the potential. The potential energy is equal to Q times V. This is what I have here. But since E has a negative sign and V is negative, the total kinetic energy is, the total potential energy is positive. So this is a higher potential energy in the anode than in the cathode, and this reverse, because this guy is negative with respect to that, is due to the fact that the charge of the electron is negative. Okay, so that is simply the asymmetry here. So if I put a negative voltage here, you can definitely have the feeling that if this voltage is very high, the electrons are going to be repelled. And I have this diagram as a function of distance here. So this may not be a linear dependence. It really depends on the shape of the thing. It may be something different. If the geometry is somehow circular, that may be the case. Okay. But as you can see that if this guy has this kinetic energy at the surface of the cathode, it could start traveling towards the anode, but at one point it could arrive at this point of potential energy, and so what will happen with the kinetic energy of that thing will be zero, because all the energy that it has at the beginning will be transformed in potential energy. And what will happen if the thing is there? Well, it would feel the force of the difference in potential and will go back. That's what will happen to the electron. But then there could be electrons that have high enough energy above the value of this guy, and those guys will make it and could be measured. So that is the way. That is why you have a constant intensity, a constant current measuring this meter over there. This I is the same as this I over here. You measure a constant value for positive voltage. The only limited here is the number of electrons that you have, and the number of electrons that you have are only limited by the intensity of the light. Okay, but then when you reverse the voltage, what happens? Well, the current starts to decrease, because some of the guys, the ones that have less energy, will be rejected. Only the ones with very high energy will go by. And then at one point, even the guy with the highest energy available is not going to be able to come out. Okay, it's not going to be able to be collected at the anode. It will come out of the cathode, but it won't be collected at the anode. Okay, so that's the thing. Let me go to the next one. This is another piece of information here. This is a stopping. Oops, let me get this guy out of the way. Okay, so this is the graph of the stopping potential as a function of frequency for a particular cathode material. So the interesting aspect here is that if I raise the frequency of the light, you need to go further negative. The energy, the repulsion energy, potential energy is higher when the frequency of the light is higher. So the maximum kinetic energy that a particle coming out of the cathode can have is increased when I increase the frequency of light. This is also part of the puzzle. Okay. The next one is the following. The value of the stopping potential is highly dependent on the material. Meaning, if I have a material 1, this one over here, I can have a stopping potential. This V naught, this is a stopping potential, which is actually small. But when I go to a different material that has a phi 2 that is different, the actual value is higher. And for a particular material, you cannot change materials while doing an experiment. So what you do is you change the frequency for a particular material, you get this graph. And then you change the material at the cathode, and you get a different value. So you get a parallel line going, around here. Okay, that's what happens. Okay, this was sort of the information, probably not as detailed as what I am describing, that Einstein had as evidence when he proposed a model, okay, to describe the photoelectric effect. So he actually came up with this weird idea, that again, that light, instead of being or being able to be described by waves, can be described as particles. And these particles, with as it says here, with no mass, have energy and momentums. Okay, this way of describing the photoelectric effect, not as a wave, not handling the light as wave, but as photons, you know, it was way ahead of the time. This is quantum mechanics before quantum mechanics. Okay, so this Einstein model proposed, the whole quantum mechanics had to be developed, and then a forward branch of quantum mechanics, which is quantum electrodynamic, has to be developed, which is sort of probably 50 years after Einstein proposed this model. Is that somebody came along with a model to describe excitations of light as a quantum phenomena. So the model that Einstein proposed is the following: light is actually made of photons, and you can see this guy is a particular photon here, and each photon, depending on its color, carry a certain pack of energy. So they also carry momentum, but they have no mass. That's why it's so thin, this guy. But they have an energy. They have this backpack with energy here, and the energy is actually proportional to the frequency of the photons of the light. So the higher the frequency, the higher the energy the particles, the photons carry. So when I have the collision of a photon, a particle of light, with an electron, this is the before thing, and in the after thing, the photon is gone as a particle. It disappeared, but it has delivered all the energy he has. This h nu he was carrying in the backpack, he delivers it to the electron that runs away with a kinetic energy equals to h nu. Okay, nu is f, is the frequency. Okay, so this is the model. You know, it sounds really weird to what we have been doing before, how this is compatible with the light being a wave. Well, light is light. Okay, and light behaves in different ways depending on the circumstances. Sorry. When we have a light interacting with matter, the particle picture is the one we need. When we have light interacting with the objects and transport, is the wave phenomena that counts. Okay, so this is exactly what goes on. So the energy of the photon now of this particular guy is h nu. This is the frequency of the light, and this is a constant. This constant is independent of the value of the frequency. That's why it's a constant, and it's a universal constant, and it's called the Planck constant. Okay, the intensity of light is the intensity of the light. Now I'm trying to make the connection with what we were seeing before, and describe the intensity as the flux of energy per unit time that arrives to a surface. Okay, per unit time and unit area, essentially. So is the energy per unit area, per unit time that arrives at a surface. So I have a model here. Remember that this is a flux. Now light, instead of a wave, you can think it as a collection of particles. These particles are massless, so they have no rest mass. The photons have no rest mass, and they are colliding with the surface, the green surface here. So the idea is how many photons go through this area per unit area per unit time. That will be the intensity of the light. So if in an interval delta t, all these guys that are in this volume here will cross the area here. So in delta t, the amount of energy that crosses the green area will be the volume. The volume is A by the area, C times delta t is the length. So this is the volume of the cylinder here. And now inside this volume, I have a density of photons. This is n, the density of photons. And each photon has an energy h nu, because this is the backpack that each photon carries. So this will be the total energy that crosses that surface area in the unit of time. So the intensity will be the E and delta E divided by A delta T, and that is equal to N times C times H times nu. Because, you know, I take this expression and divide by the A and the delta T, and you get this expression. So the intensity is proportional to the density of the electrons and the frequency. And this is the model, the photon model. You have to be reminded that in the wave picture, this is what we did. We did something that was around here, and we defined the intensity I as this expression, where we take into account the time average and the relations between the Maxwell the thing that comes from the Maxwell equations and the wave equation, that is the size of the beat related to the E field. And so I can write it this way. This thing here is equivalent to this thing here. So if I look at the two things, it means that, yeah, this term here, if take out the C, this term here, the amplitude square is of the field is somehow proportional to the density of photons times the frequency. Okay, so this is the equivalence between the photon picture and the wave picture in terms of intensity. Okay, so somehow you can associate the square of the field with the product of the frequency times the density. Okay, that is you know, an interesting aspect of this. Okay, let me go to the next picture. Now I have a problem. The second problem is you know, let me go back to here. See, this no, to this graph. So somehow the maximum energy that the electrons can have, which is equal to the stopping potential, is higher in some materials than another. So there is a material dependence here. So if there is a material dependence, we have to somehow get a model for the material dependence. Okay, we have to get a model for the valence band electronic structure of the material. Okay, perfect. So this is it. I have a model for the valence band of the electrons in a metal. Okay, so this is a diagram of energy versus position. So the boundary between the metal, which is here, and the outside of the world, the vacuum, is at x equals 0. So this is a one-dimensional model. So in the negative values, we have the metal. In the positive value, we have vacuum. We have nothing. Okay. So if we draw here the electrons, this is a good model, and we're going to see that this model is consistent with all the rest well-known physics on the subject. All the valence electrons in the metal are somehow living in some sort of inside a potential pool. They essentially they are in a bath of electrons here, and all the electrons live between the bottom of the band. This is a band of, it's called an energy band, and they are allowed to be between a maximum value, which is this top here, and the bottom of the band, and they are all caught there, and they cannot go out, because under normal circumstances the electron stick inside the metal, they don't come out of the metal. Okay, really, to get them out, you really need to excite them over the barrier that keeps them in. So essentially, if I want to take an electron out, I have to get the electron from here and deliver enough energy so it could go free from the material. Okay, so W or phi, this value here is called the work function. Okay, this W, I wrote something up somewhere that is also the same thing. Okay, so the book has W. I'm sorry, the book has phi, the Greek letter phi, and I use W. And in the case of the voltage, the book used F, and I use the Greek letter nu, and they are all exactly the same. Okay, so essentially what happens here, we need to let's say we're interested in getting this electron out. If we get this electron out, this electron has to absorb energy, and I say the only thing that I'm doing is I'm photoexciting. So I have some light that comes in, gives energy to this electron, and how much energy does it give? Well, h nu is the value of the electron. So I promote this electron that is sort of very high lying here at the bottom of the well of electrons inside the metal, and I promote it up here by h nu. And now this guy can travel inside the metal going that way, or can also go outside the metal by going this way. The fact that they are equally probable, it means that some electrons will have the probability of leaving actually the piece of metal if they are excited up here. Okay, and I'm only drawing the one that are going out. Okay, and the question is, what is the kinetic energy of this guy? Well, the kinetic energy of that guy will be exactly equal to the energy given. So this guy gained how much energy from the bottom here? It came up here by absorbing the energy of a photon. It went out of the metal, but for that it has to overcome this potential barrier that's here. So essentially, the kinetic energy outside of the metal will be the difference between the actual kinetic energy and the potential of the vacuum energy level. That's it. That's the difference. So if the energy of this guy was right enough to get it at this energy level, it means that it will have a kinetic energy equal to 0. It means it won't go anywhere. Okay, it won't go out the metal because it will have to come out with 0 kinetic energy. But as soon as it has a little bit more energy than that, it will come out. Okay, that's what it is. So again, this is the outside of the metal. X greater than 0, X less than 0 is the inside. And what is the kinetic energy for this process? This is the famous Einstein formula here. So the kinetic energy of the electron coming out of the metal is equal to h nu, the energy that a photon can provide an electron to make a transition to a higher energy state, minus W. What is W? W is the difference from this level, the vacuum level, to the highest occupied energy inside the metal, This level here is called the Fermi level. It's an energy level inside. This is the highest occupied energy level of the electrons inside the material. So that is W. Minus EB, which is the binding energy, which is the energy below the Fermi level, is actually occupied by the electron, in this particular case by EB. Okay. The useful thing is to measure all the energies in electron volts. Electron volts are a unit of energy, as you studied in Phys 120. It's really at the atomic scale. 1 electron volt is the kinetic energy that a particle can acquire by moving through a potential difference of 1 volt, having a charge of 1 electron, the charge of 1 electron, it will acquire an energy of 1 electron volt. Okay. What I'm trying to do next here, please watch this video here, because it provides some simulation. Maybe you're going to be using this in your experimental in numerical experiments that you will be doing, but look at this because it's very instructive. It's a nice simulation of the photoelectric effect done on a movie, and you can actually log in, and I encourage to do that. Download the app to perform the simulation yourself by changing the parameters that you want and see how you can obtain the curves that I actually display in the first part of the class. Okay. So this is the photoelectric effect in numbers. I just want to put some numbers down because it's useful to have an idea of the magnitude of things. The value of the Planck constant is 6.63 times 10 to the minus 34 joules per second. So you can see that this is a very small number. Okay, so you really need to get a very high frequency, optical or beyond, of the light. Radio waves that don't make it, infrared doesn't make it. You really need high frequency, optical or higher, in order to get some evidence of photoelectric effect from a material. So this constant H can be written also as a way. This is one of the few numbers that I remember of all the constants in well, I remember the velocity of light is 3 times 10 to the 8 meters per second. I never remember that this is 6.63 times 10 to the minus 34. This is such an odd number, but the product of H times C, which is a useful number, with the bar, so H bar C. I also have this problem that I cannot write H without a bar. I actually rewrote this guy, I erased it and wrote it again, because H bar is equal to H divided by 2 pi. That's what the bar means, okay? And H divided by 2 pi times C happens to be a number that people from my generation remembers very easily. In 1973, which is, it's a year actually that I was alive. So this is a nice coincidence that I'm given with some advantages to actually remember this number. For you this is history anyway. The energy of a photon. The energy of the photon is equal to E. The energy of the photon is equal to h nu. This is Einstein's proposal. Okay, so let me write it again. So this is h times nu. H times nu is equal to h divided by the period of the light, t. But divided by t. So I can multiply this guy by c on top and c on the bottom, and t times c, the period of the light, times the velocity of light is equal to the wavelength, okay? And then I recover this hc up here, and I have to multiply it by 2 pi and the hc. Perfect, okay? So whenever I want to convert wavelength on energy, what I do is simply, let's say, the energy of a particle, the energy of a photon. So this is something very profound, actually. I'm just going over the numbers and thinking about it. It's the energy of light has to do with its color. Color and energy are synonyms in this picture. Okay, so a single frequency means a single color, a single wavelength means a single color, and now I want to make what is the equivalence between wavelength and energy. Hc is this number. Well, it's easy to multiply it by 2000, so I write 2000 here. This 2 pi here, it's a little bit more than 6, and this guy is a little bit less than 2000, but you know, 6 times 2000 is 12,000, which is a good round number. Okay, so you can do it with a calculator and do it much faster. But you know, if you want to have estimates of the thing, this is 6 times 2. This is 12,000 divided by the wavelength in angstrom, because you want to get the electron volts out. The energy of a green photon essentially comes out to be 2.2 electron volts. Which is, you know, anything above that is enough energy to actually remove electrons from some materials. Okay. Kinetic energy of an electron. So these numbers are relevant here in this picture. Kinetic energy this is the kinetic energy. This is, I'm talking about non-relativistic. How do I know that the thing is non-relativistic? Because the rest mass of the electron is of the order of 511 kilo electron volts. Okay, why do I measure mass in electron volts? This guy's crazy. No. Mass times c square, that is the rest mass of the electron measured in electron volts. And this is 511. So the kinetic energy of an electron, I can write this way. So I multiply here by c squared and divide by c squared. So I can write it a half the rest mass of the electron measured in electron volts divided by c squared. Okay. Let me go to the next. Okay, so what would be the kinetic energy for what would be the beta, or the value of beta for a 1 electron volt electron? So the total energy of the electron will be 1 electron volt, and this will be the mass of the rest mass of the electron divided by 2 multiplied by beta square, which is exactly this here. So this is the half, this is the 511, and this is beta square. Okay. Is 2 times 10 to the minus 3. So the beta of the particle it's really, really small. To actually get a significant departure of the energy with respect to anything, is you need this to be of the order of 0.1, 0.2. When you have 0.1, 0.2, the gamma value, which has to do with everything, and it's reasonably high enough, so you have to take into consideration relativistic effect. If that is not the case, you can get away with writing the kinetic energy in this way instead of the formula that we use during last class. So the next question is, what is the minimum energy required to remove an electron out of a piece of material? The photon, so the idea is the following. The photon should strike the less bound electron and should deliver to it enough energy to promote it to the surface with zero kinetic energy. So the picture is this one. So the more energetic electrons that comes out of a material are the ones that come from the Fermi level, from the highest occupied electron level from the bottom of the band of where the electrons can live. Okay, so what I'm trying is to answer is, what is the minimum energy required? So the energy required is going to be delivered by a photon. So what is the frequency of the photon that I need to actually take an electron out? Well, the minimum energy that I require is simply to put it in here with a certain amount of energy, with what energy equals to 0. So h nu should be equal at less to omega to be able to, or w, I'm sorry, or phi in your notes or in the book, to be able to get it out. Note that phi or w are potential energies and not voltages. Okay, so whenever you put a voltage in a energy equation, it should be multiplied by the charge. So this is exactly what happens here. Okay, so this is the potential, and now let's apply a voltage, a repulsive voltage. So if I apply a repulsive voltage, I can actually measure. So let's say I have a certain color, red, and this red guy will take an electron from this level. And what makes one material different from the other is that this W could be smaller in some cases or higher in others. Okay, that's what makes the difference between one material and the next, the size of the W. So that's what makes the difference. This is the detail that makes difference, that moves the stopping potential in one way or the other. Okay, what does the stopping potential measure? The stopping potential measure corresponds exactly to the situation that I'm showing here. Let's say I have a particular frequency of light. This frequency of light produces an electron that is excited with this type of energy level. At this energy level, the electron will get to the cathode unless I apply exactly the same voltage, which is equal to the kinetic energy. Here, what is the kinetic energy? The kinetic energy is equal to h nu, the energy given to the electron, minus w, the work function. This is phi. This is what is known as phi in the text. And that is equal to the stopping potential times E. So by identifying what the stopping potential is, what information is that giving me? That is giving me only the kinetic energy that the particle has when it comes out of the surface. It will give me exactly this thing here. So the current will be exactly 0 if this height from this level to this level is equal to the height from the vacuum level when the potential is 0 to there. So the electron will start moving towards the anode, and the kinetic energy will start reducing at the expenses of the potential energy in this direction until it gets here with 0 potential energy at the surface. And what will happen to that guy? 0 there, it will come back. So it really needs to have a bit more energy to come out, or the potential should be a little bit lower, and the electron will of the highest energy that I can pull out. Because if I pull out this electron with the same frequency of photons, it will arrive, not as high as this one. This is the highest kinetic energy of the particle. This is why at the end, when we apply the repulsion curve, let me see this guy. This is why they all die at the end. Okay, because this is a single frequency measurement. That's something you have to be reminded of. Okay, I think we are 25. I think we are done. Okay. I will upload this thing here in your notes, so you will have them. Is this the same graph? Yeah, we were here. No, we were not here. We were here. I copied the same graph in the other side. Okay. So I guess what do I want to do? What do I want to tell you guys? So this is the work function for several materials, and you can see how they vary. Okay, so this explains why with material 1 and material 2 you get different stopping potentials, because for a certain light, for a certain frequency, this is frequency 1 and frequency 2, you know, this is frequency, I'm sorry, this is the different material, you will get different kinetic energies of the particles at the surface of the material. So this is what explains the difference. Now, I want you guys to oops, no, where am I? Here. Okay, we're going to see X-rays next class, but I would like you guys to consider this homework here that I'm giving to you. Take a good look at this, and well, this I've already explained this to you, so there's no, you know, I don't have to go into the details of that. But I would like you guys to check this out to actually, you know, get the information you need to actually solve this problem. The radio at the university emits power of 10 to the 4 watts. You know, that's the power that it emits in radiation. And I'm asking you that you assume a uniform distribution of the power in all directions as a function of distance, and estimate well, what is this uniform is, it's not as a function of distance, actually, as a function of direction. This is incorrect here, as a function of direction. Okay, no matter where the power is emitted, it is a uniform distribution of power in all directions. That's what it means here. Yeah. So I say estimate as a function of distance the density of photons 1 kilometer away from the antenna, the work function of a material that can exhibit photoelectric effect due to the radiation emitted from the radio. Find out if there's any material that can do that, and compare the value in B with the minimum value known for the work function of elements in the periodic table, and comment. Okay, so you know, do some research on that. I'm going to go into production of X-ray next time. Okay, so my compromise is to actually try to get all uploaded or everything in the correct way in your classes, and everything is going to be in YouTube anyway. So as soon as I can get them there, okay, I have to stop this recording and generate the video out of it. So I guess I will be seeing you guys in you know, a week and you know, 5 days from now, okay, because I guess you all have vacation next week. So this is it. This is the class for today. If it's not clear enough, please read it, because this not in the note but in the book, because this thing is actually important that you learn. Okay, all the exams have a photoelectric effect question, and I don't think I'm going to be an exception. Okay, so go ahead and do something about it, learn it. Okay. Okay, so let me stop the annotate. Okay, and let's stop the sharing. Okay. And now what I need to do is stop recording.